Good evening, or good morning, or silent night, depending on when you're listening to me. Close your eyes for a moment. Feel how your body sinks into the chair, into the bed, onto the grass beneath the stars. Breathe in slowly, and breathe out. Once more. Let your shoulders relax, let your arms become heavy, and your thoughts light, like little clouds drifting by. I'm your guide on this quiet cosmic journey. Today we're not rushing. No formulas, no dates, nothing you need to remember. Just us, the sky, and the stars whispering their stories. I'm sitting here in a warm room with a cup of herbal tea. Outside the window, a gentle breeze rustles the leaves. And you? Where are you right now? Maybe on a balcony with a blanket over your shoulders? In a car after a long day? Or just in your headphones, lying on your back and staring at the ceiling? Tell me in your thoughts, what did you do today? Maybe you had coffee with friends, walked your dog, read a book, or just looked out the window. I woke up early today, went out to the yard. The sky was still gray, but one star was already twinkling. I thought, there it is waiting for me. And I decided that today you and I would journey to it, without hurrying. Step by step, cloud by cloud, imagine. We're lying on a soft blanket in the middle of a field. All around, silence. Only crickets and the distant rustle of trees. Above us, the Milky Way, spilled like milk across black velvet. Not a single city light, only stars, near and far, bright and barely visible. Each one its own story, each one its own breath. Today we won't be learning. We'll be listening, feeling, breathing the cosmos. Ready? Then breathe in once more and allow yourself simply to be. We're beginning. Imagine an infinite cosmic ocean where light, cool clouds slowly drift. These are stellar nebulae, gigantic blankets of gas and dust drifting in the silence of interstellar space. They're cold, just 10 to 20 Kelvin, and enormous, tens of light years in diameter. 99% of the nebula is hydrogen and helium, and the dust is less than a micron. These clouds seem calm, but life is already being born within them. Dust blocks the light of distant stars, making the nebula dark like a night blanket over the Earth. This very dust hides from us the first steps of newborn stars. Now gravity enters the game, a quiet but relentless force. It slowly, like an invisible hand, squeezes the cloud toward the center. Gas gathers, density grows, and the cloud begins to collapse. This takes millions of years, a slow, almost meditative dance of particles. Gravitational collapse is millions of years of compression. At the center, a dense sphere forms, a protostar. It heats up from the compression itself. Temperature rises to thousands of degrees. The protostar glows with a soft infrared radiance, hiding behind dust like a lamp beneath thick fabric jets. Thin streams of gas burst from its poles, clearing a path through the nebula. When the core of the future star becomes hot enough, thermonuclear reactions ignite. Several hydrogen nuclei merge into helium and release energy. This is the birth of a real star. Light disperses the nebulous cocoon, and a new stable flame appears in the sky. Stars are most often born in so-called stellar nurseries. The most famous places are the Orion Nebula, where a visible group of young stars called the trapezium is noticeable. The Eagle Nebula with the pillars of creation, where protostars hide in dark columns. The Carina Nebula with the bright and unstable Eta Carina and its blown-out cloud. The Lagoon Nebula, pink, warm, with a young cluster and gas bubbles from hot stars. All these regions are great factories of luminaries. The birth of a star is not an explosion. A cloud of gas and dust is compressed by gravity, heats up, and a protostar with a disk appears. Material from the disk slowly falls onto it, triggering brief bursts of brightness. The star rotates faster, flattens, but gradually reaches equilibrium. When thermonuclear reactions become stable, the star enters a long phase of quiet life, the main sequence, where it spends almost its entire age. Near newborn stars, dust disks often circle, embryos of planetary systems. In the Orion Nebula, you can even see proplyds, compact cocoons with disks illuminated by neighboring young stars. Young stars of the T Tauri type are just like that, with disks, with flares from accretion, with thin streams of matter that pierce the surrounding gas. Such streams leave noticeable traces. Herbig-Haro objects. Massive stars appear quickly and live briefly. Small ones are born more slowly, but stay on the main sequence many times longer. Inside heavy luminaries, reactions work along a heavier path. In lighter ones, a simpler chain of proton fusion. When the largest stars complete their lives, they explode as supernovae and scatter heavy elements around, material for future clouds, planets, and ultimately life. The circle closes. Nebula leads to star, leads to supernova, leads to new nebula. What helps or hinders birth? In molecular clouds, the coldest and densest regions, there are enough molecules to give off heat and allow gas to stick together in clumps. Turbulence breaks the cloud into pieces from which many separate stars form. Magnetic fields, on the contrary, slow down collapse and make the process smoother. Orion is clearly visible in winter. The nebula below the Hunter's Belt is noticeable even with binoculars. The pillars of creation in the Eagle are a famous shot from space telescopes. In the infrared range, hidden protostars are visible there. In the lagoon in Carina, the pink color comes from ionized hydrogen, which glows under the ultraviolet of young stars. And most importantly, the first light of a star is not a flash, but a calm dawn. From a quiet embryo in a cold cloud to the steady radiance of a mature star that holds its planets and warms them for millions and billions of years. If you want, I can similarly shorten some separate sections or make a very short version in one page. A star spends most of its life in a calm phase called the main sequence. In the core, thermonuclear reactions proceed. Hydrogen transforms into helium and gives light. Part of the mass converts to energy. This is exactly how the star burns. Energy from the depths rises outward very slowly. First, it wanders inside, being absorbed and re-emitted. Then warm currents carry it upward like boiling liquid. On the surface, in the photosphere, we already see light. The star is held by a delicate balance. Gravity tries to squeeze everything inward, and the pressure of hot gas and radiation pushes outward. This is equilibrium, neither explosion nor collapse. Turn off thermonuclear fusion, and the star will quickly shrink and heat up. Color depends on surface temperature. Cooler ones seem reddish, middle ones yellowish-white, the hottest bluish. The hotter, the bluer. Most luminaries in the galaxy are quiet red dwarfs. They're small, economical, and live very long. Blue giants are rare but shine stunningly bright. The nearest star to us, Proxima Centauri, is precisely a red dwarf. Why do stars twinkle? Actually, it's our atmosphere trembling, like a thick layer of water. In its turbulent layers, the ray bends and straightens, and the star winks. From space, this doesn't happen. There, starlight is steady. Inside a star, two main engines work in lighter luminaries, a simple proton-proton chain. In more massive ones, the CNO cycle, where heavier elements serve as catalysts and speed up reactions. In any case, the result is one, energy that feeds the radiance. The life of a star doesn't stand still. When fuel in the core is exhausted, the central layers compress, the shell swells, changes begin, but that's later. Now, enduring stability. Our sun is somewhere in the middle of its path. The Hertzsprung Russell diagram is like a passport. On one axis temperature, on the other luminosity. Most stars sit on a diagonal ribbon. This is the main sequence, while hydrogen burns in the core. Rotation adds character. Young stars spin quickly. With age, they slow down. Rotation generates magnetic fields. Spots and flares appear. The sun's period at the equator is approximately 1 month, and this also affects weather in space. The surface of the sun is grainy. These are convective cells, each larger than a country, the result of plasma boiling. Astronomers literally listen to stars. Sound waves inside make them barely pulsate. From these waves, you can learn the structure and age of luminaries. Even when a photon breaks through the thickness of a star for a very long time, it reaches us directly, and we see yesterday's, today's, and ancient sky in one frame. Convection in the shell mixes matter. In red dwarfs, they're fully convective, so they live long. In giants, a thin layer. In fully convective ones, hydrogen is mixed. Fuel lasts a long time. The light of a star is not just photons. These are neutrinos that fly through Earth without noticing. Solar neutrinos are proof of thermonuclear fusion. The Super Kamiokande detector catches them in a mine. Does a star pulsate? Some do. Cepheids are variable, pulsating for days. They're used as standard candles. Measuring distances in the universe, Henrietta Leavitt discovered the period luminosity relationship in 1912. Binary stars, a dance for two. 50% of stars are pairs. They orbit, exchange matter, influence evolution. Algol, an eclipsing binary, the demon star. Magnetic fields are invisible forces that shape the star's behavior. They slow rotation, create streams of charged particles, twist coronal loops that we see during solar flares. The solar wind is a continuous stream of plasma spreading into space. It carries particles at speeds of hundreds of kilometers per second and fills the solar system with an invisible sea of charged gas. The atmosphere of a star has several layers. The photosphere is what we see as the surface. Higher is the chromosphere, glowing pink during eclipses, and above it is the corona, heated to millions of degrees. Despite the paradoxical temperature, the reason for its heat is in magnetic waves that heat the plasma from above. Stellar wind can be gentle, but it can become a storm. The sun's is relatively weak, but in giants, it's so powerful that it blows off outer layers. There are special stars, Wolf-Rayet type. These are cores that have already shed their shells. Their wind is furious. They emit powerful ultraviolet and gamma radiation. Such stars are harbingers of supernova. Mass determines the fate of a star. Everything depends on it. Color, temperature, lifespan, even how the star will end its existence. Too little mass, and reactions won't start. A brown dwarf forms. A bit more, a red dwarf. Dim but almost eternal. Stars like the sun live calmly and long, and massive giants brightly but briefly. The more massive the star, the brighter it shines, and the faster it burns out. Our sun is a calm yellow dwarf. It's currently in its most stable state, a true model of equilibrium. One day it will swell into a red giant, but now it's in its prime. In 1 second, it produces as much energy as billions of hydrogen bomb explosions. The most common stars in the galaxy are red dwarfs. Their calm and economy make them potential eternal luminaries of the universe. On the opposite pole are blue giants, hot, dazzling, with destructive ultraviolet. They're short-lived, but they are the ones who form the chemical richness of space after supernova explosions. No star exists in isolation. They're born, live, and die in community, in clusters, galaxies, among dust and gas. Our Milky Way contains countless stars, each with its own story, and each sends into spacelight, carrying its signature, the spectrum. In these thin lines hides all information: temperature, composition, motion. Light is the speech of a star, its way of telling what it's made of and how it lives. Spectroscopy is like the DNA of stars. Variable stars, heartbeats, Mira variables pulsate for months, RR Lyrae for hours, Cepheids, the key to the scales of the universe. A star is a furnace. It burns hydrogen, produces helium. Helium accumulates, the core compresses, the shell heats up. But this is the end of the main sequence. When hydrogen runs out, the star will sigh and swell. But now, calm. The star shines. We see light that has traveled for years, millennia, millions of years. Each star is a story, quiet, stable, but full of energy. It shines because it burns. It burns because it lives. Our sun is no longer young. It's 4.5 billion years old, and there's enough hydrogen in its heart for just as much more. One day, in 5 billion years, when we'll long be dust, it will feel emptiness in the center. The thermonuclear fire fades. Helium that has accumulated, like ash in a stone, doesn't burn gravity, which all this time held onto the pressure of reactions, suddenly takes over. The core compresses, slowly at first, then faster. Over tens of thousands of years, it will shrink by hundreds of times. The shell, still full of hydrogen, reacts in reverse, swelling. The sun becomes a red giant. Its surface will cool to 3,000 degrees, light will redden, and radius will reach Earth's orbit. Mercury and Venus will disappear in its depths. Earth, if it survives, will become a scorching desert with molten oceans. Mars, on the contrary, will feel warmth. Hydrogen now burns not in the center, but in a thin layer around the helium core. This is unstable fire. The star begins to breathe, expanding, contracting pulsations. Brightness fluctuates. In the sky, the sun will flare up, then dim. Such stars we already see: Arcturus in autumn, Aldebaran in winter. They were giants when the Egyptian pyramids weren't yet standing. When the core heats up to 100 million degrees, a flash will occur. Helium ignites. 3 helium atoms merge into 1 carbon. This is the triple alpha process. In small stars like our sun, the flash is sudden, within minutes. In massive ones, gentle, gradual. The star seemingly inhales a second life. It enters the helium-burning phase, the horizontal branch. 100 million years of calm, but helium burns out faster than hydrogen. Then, massive stars go further. Carbon with helium gives oxygen. Oxygen, neon. Neon, magnesium. Magnesium, silicon. The core becomes multi-layered, like an onion. Each element burns in its own layer. Outside, chaos. The shell is swollen, unstable. Stellar wind intensifies. The star sheds outer layers slowly, like an old coat. Planetary nebulae form: ring, dumbbell, cat's eye. Shapes depend on rotation, magnetic fields, sometimes on an invisible companion. In small stars, the path is simpler. After helium, the core compresses for the last time. The shell flies off as a nebula. A white dwarf remains, the size of Earth, mass half that of the sun density, 1 ton per cubic centimeter. Hot at first, then cools for billions of years. Eventually, a black dwarf. But there aren't any yet. The universe is young. Massive stars don't give up. Silicon merges into iron. Iron is the end. It doesn't give energy, it takes it. Thermonuclear fusion stops, gravity wins. The core collapses in seconds. Temperature, billions of degrees. The shell explodes as a supernova, brighter than a galaxy. A neutron star or black hole remains Betelgeuse in Orion, a red supergiant, 100,000 times brighter than the sun. It pulsates. In 2019 to 2020, it dimmed, a dust cloud or harbinger of explosion. Eta Carini in Carina, even bigger. It exploded in 1843, ejected 2 solar masses of gas, still alive but unstable. In supernovae, heavy elements are born: gold, silver, uranium. Rapid neutron capture, R process. Carbon in your body, calcium in bones, iron in blood from supernova that exploded before the sun's birth. A GB stars on the asymptotic branch synthesize technetium, radioactive, lives thousands of years. But in their atmosphere, it exists, meaning just created first proof that stars are living laboratories. 97% of stars will end as white dwarfs, massive ones, supernovae. They enrich space with metals. Our nebulae are not the first generation. That's why there are planets. That's why there's us. A star ages and gives. A planetary nebula, the last song a white dwarf, an eternal memory, a supernova, a new beginning. The cosmos doesn't die, it's reborn, star after star. The mass of a star is its fate. Everything depends on it, how long the star will live, how it will evolve, and how it will end. In the galaxy, most stars are small. but massive ones make the greatest contribution to the cosmic cycle. Let's look at how this happens. Stars with a mass up to 8 solar masses go through a calm path. The Sun is a typical example. After the main sequence, it will become a red giant, shed its shell, and leave a white dwarf. The lifespan of such stars ranges from several billion to trillions of years for the smallest. When thermonuclear reactions in the core fade, the star loses resistance against its own gravity. Outer layers slowly fly off, forming a luminous cloud, a planetary nebula. Its shell shines thanks to the ultraviolet of the heated core. In old telescopes, these nebulae really resembled planets, hence the name. What remains in the center compresses to Earth size. Electrons in tight space create a special pressure that stops further collapse. Thus appears a white dwarf, hot, dense, but already without an internal energy source. Over time, it simply cools, dims, and eventually will become a black dwarf. Though we haven't yet managed to see such, the universe is too young. This is exactly how our sun will complete its life, shed its shell, form a nebula, and in the center will remain a small but extremely dense core. Massive stars live completely differently. They quickly go through all stages of nuclear synthesis up to iron. But at iron, the process stops. Reactions with it don't release energy, and the core can no longer withstand its own weight. In a moment, it compresses to an ultra-dense state. Temperature soars to incredible values, and a stream of neutrinos carries almost all energy outward. The shell falls back onto the core, bounces, and explodes. Thus is born a supernova, the most powerful event in the universe. The explosion shines brighter than all the stars in the galaxy combined and echoes for thousands of years. Everything that remains after the explosion depends on the star's mass. Less massive ones form neutron stars, dense as an atomic nucleus, the size of a city, rotating incredibly fast. Some of them, pulsars, send regular pulses of light and radio waves into space, more precise than any clock. And when the mass is even greater, nothing can hold back the collapse. A black hole is born, space and time curl around it, and even light can't escape. Supernovae are true creators of chemical diversity. In ordinary stars, elements are synthesized up to iron, and heavier ones, gold, platinum, uranium, are born precisely during the explosion. When a star's core explodes, it instantly captures streams of neutrons, and from this nuclear chain, new atoms arise. That's why all the gold and silver on Earth is the legacy of ancient supernovae. When such explosions scatter heavy elements into space, they don't just fertilize space, but also trigger the birth of new generations of stars. Waves from supernovae compress cold gas clouds, prompting them to collapse. From these fragments, new stars, planets, and perhaps life are formed. Sometimes medium-mass stars explode more weakly or even disappear without a flash, simply collapsing into darkness. In the sky remain only remnants of nebulae, like Cassiopeia A, a scar of an ancient explosion still glowing with hot ash. In the galaxy, 100 supernovae per million years, but visible ones are rare due to dust. Small stars fade quietly, massive ones explode, scattering elements. We are from this ash. Every star's death is a step toward a new generation. When a star dies, it doesn't disappear, it transforms. Something dense, hot, extreme remains, an object that violates all earthly notions of matter. White dwarf, neutron star, black hole, these aren't just remnants. These are new worlds with their own laws of physics, histories, and roles in the galaxy. They affect everything, from magnetic storms on Earth to the birth of next generations of stars. A white dwarf is the sun compressed to Earth's size. Its mass is hundreds of thousands of times greater than Earth's, but volume is like our planet's. A crumb of such matter weighs like a truck. It's born from the exposed core of a red giant when the star can no longer burn hydrogen and helium. Electrons there are compressed to the quantum limit, Their pressure holds the star from further collapse. There are no thermonuclear reactions, only slow cooling. At first, the dwarf glows white-blue, then yellows, reddens, and fades. Eventually, it will transform into a black dwarf, but the universe is still too young for us to see even one Sirius has a companion invisible to the naked eye, a white dwarf. Once it was a massive hot star that quickly lived its life, shed its shell, and compressed. Now its core is dim, invisible light, but very bright and ultraviolet. A similar story has Procyon b, a white dwarf in a wide orbit, known to astronomers since the 19th century. White dwarfs are the most common stellar remnants. There are countless of them in our galaxy. In globular clusters, they work as clocks. Cooling curves determine the age of these ancient star cities, close to the age of the galaxy itself. Part of dwarfs, as they cool, crystallize, carbon and oxygen build a lattice, essentially a cosmic diamond. One of the first known such objects is in Centaurus, which gave rise to the joke Lucy in the Sky with Diamonds, I'll add. If a white dwarf in a pair eats its neighbor and exceeds the critical limit, it can explode as a standard candle, a type Ia supernova. These are precisely what are used to measure cosmic distances, the extreme path, neutron stars. They're born when massive stars complete their lives in a supernova explosion, and the core compresses to city scale, preserving the mass of most of the sun. Protons and electrons merge into neutrons. Density is like an atomic nucleus. A spoonful of such matter would weigh a mountain of metal. Outside, a thin, solid crust beneath it, liquid of neutrons in the heart, possibly even more exotic matter. They rotate insanely fast, from a heartbeat to the trembling of a wheel, and have fields many times stronger than anything we can create on Earth. Some of them, pulsars, beacons that regularly click in radio and X-ray ranges and serve as ideal chronometers. In short, white dwarfs are quiet embers cooling long. Neutron stars are ultra-dense rotary beacons. Together they tell how stars age, crystallize, explode, and leave behind the most bizarre objects in the universe. A newborn neutron star rotates hundreds of times per second. Conservation of angular momentum, like a figure skater pulling in their arms. In the constellation Taurus, a supernova once flared, which Chinese astronomers saw in 1054. They recorded. A guest star appeared, visible during the day. From it remained the Crab Nebula, a cloud of hot gas spreading in all directions at its heart. A pulsar, a neutron star spinning madly and pulsing in radio, X-ray, and gamma radiation. It feeds on the energy of its own rotation, gradually slows down, but will shine for millions more years. In 1967, graduate student Jocelyn Bell in Cambridge detected regular pulses, even repeated, like a metronome. At first, they thought about a signal from aliens, and even gave the name LGM1, Little Green Men. But it quickly became clear, it's a pulsar, the first evidence of the existence of neutron stars. Among them are also magnetars, stars with an incredibly strong magnetic field. Their bursts cause short but powerful flashes of gamma radiation, the energy of which in a moment surpasses everything the sun emits over thousands of years. Neutron stars are natural laboratories where gravity, magnetic forces, and matter density reach the limits of the possible. And when a stellar core is too massive, no pressure holds back the collapse. Everything compresses to a state where space and time lose their usual meaning. Thus is born a black hole, a singularity hidden behind the event horizon. For an external observer, anything falling there seems to freeze forever. Such star ashes have masses from several to tens of solar. A classic example is Cygnus X1, a binary system where gas from a companion star falls onto an invisible object, heats up, and emits powerful X-rays. Theoretically, black holes can slowly evaporate through Hawking radiation, but for them, this process lasts so long that practically they're immortal. White dwarfs are like smoldering embers. In binary systems, they can steal matter from a neighbor. If the mass exceeds the critical limit, a type Ia supernova will flare. The star disappears completely, leaving a bright trail by which astronomers measure distances in the universe. The most famous explosion of this type was seen back in medieval times, the supernova of 1006, the brightest in the history of observations. Neutron stars, on the contrary, aren't silent. Pulsars blink evenly, serving as precise cosmic clocks, and magnetars from time to time explode, tearing space with the most energetic light in the cosmos. Thus ends the story of massive stars, either with the quiet heat of a white dwarf, or the flash of a pulsar, or the black silence of the abyss. Mergers with black holes, sources of gravitational waves and heavy elements, our process. Black holes, gravitational engines, in the centers of galaxies, supermassive ones, millions to billions of solar masses, Sagittarius A star, in the center of the Milky Way, 4 million solar masses. Photo from 2022, Event Horizon Telescope. Black holes seeded galaxies. Their jets accelerated gas regulated star formation. In the Orion Nebula, young stars. Nearby, supernova remnants. The shockwave compressed the cloud and a new generation was born. Every death is a contribution. White dwarf, a calm end neutron star, an extreme beacon. Black hole, silence that swallows everything. But together, they keep the galaxy alive. When we go outside at night and raise our heads, the sky seems like a dome studded with thousands of motionless lights. These lights are stars, distant suns burning in interstellar space. But much of what we see and feel is an illusion or ancient history. Falling stars don't fall. Stars move, though we don't notice, and light from them travels for years or millennia. People for centuries explained these phenomena with myths, then with science. In this section, we'll go through everything in order. What falling stars really are, how the perception of stars changed from legends to telescopes, why the starry sky seems static though everything is in motion, and how exactly the light of distant luminaries reaches us. Falling stars aren't stars at all, but small fragments of stone or metal crashing into the atmosphere. When they burn up, we see a brief flash, a meteor. This can be a grain of sand or a tiny fragment left over from a comet or asteroid. Moving at speeds of tens of kilometers per second, it compresses the air ahead, it heats up, and the particle flashes, leaving a glowing trail. Most meteors burn up completely high above the ground. Only larger fragments reach and fall as meteorites. Every day, our planet receives a whole portion of such cosmic dust, though we notice only the brightest flashes. When Earth passes through a stream of debris trailing behind a comet, the number of meteors sharply increases. Thus, meteor showers form. The most famous of them are the Perseids in August, the Geminids in December, and the Leonids in November. They're named after the constellations from which the flashes seem to fly. Sometimes such streams are extremely dense, the sky literally peppered with fiery streaks. This is exactly what happened during the famous Leonids in the 19th century, when residents of America thought the world was ending. In reality, Earth simply passed through a dense band of comet dust. Meteors remind us that space isn't empty. We constantly cross the trails of old comets, and each falling star is a fleeting greeting from distant corners of the solar system. People always looked at stars and tried to understand them. At first, these were myths and legends. In ancient Egypt, Sirius, the star of the goddess Isis, signaled the flooding of the Nile. When it appeared before sunrise, a new year began. The pyramids in Giza are aligned with Sirius and other stars. In Greek mythology, Orion is a hunter killed by a scorpion, so the constellations Orion and Scorpius are never visible together. The Pleiades, 7 sisters, one of whom, Merope, hid in shame, so we see 6. In Homer, stars are landmarks for sailors. The Maya built observatories and accurately predicted the movement of Venus in eclipses. In China, the supernova of 1054 in the constellation Taurus was recorded as a guest star, bright during the day for 23 days. This is the birth of the Crab Nebula. In Ukrainian legends, the Milky Way is the road of Chumax, the Pleiades are a hen with chicks, Sirius is a werewolf. The tradition of making a wish on a falling star comes from ancient times when it was believed that at that moment the sky opens. With the advent of telescopes, everything changed. Galileo Galilei in 1610 directed his telescope at the Milky Way and saw, it's not the milk of gods, but millions of stars. Edwin Hubble in the 1920s proved that some nebulae are separate galaxies. Harlow Shapley, using globular clusters, determined that the sun isn't in the center of the galaxy. Today we know stars are plasma balls on thermonuclear fuel. But myths didn't disappear, they became part of culture. Stars seem motionless because they're too far away. The sun races around the center of the galaxy, other stars too, each in their own orbits. But in the sky, all this is like a slow dance in extraordinary perspective. Changes are noticeable only with instruments. Even the nearest worlds, like Proxima Centauri, shift in the sky so slowly, as if someone is moving a coin at a distance of hundreds of kilometers. The record holder for noticeable gliding is Barnard's star. Over a human lifetime, it will barely crawl its own moon diameter in the sky. The motion of stars can be transverse, proper, and along the line of sight. Some approach us, others move away. This is visible by the shift of spectral lines, the Doppler signature of their speed. This is exactly how we know in which direction our sun is heading, toward a direction lying somewhere in Hercules. Light needs time to arrive, so we see Sirius in the past, as it was several years ago, Betelgeuse as it was in the lives of distant ancestors, Deneb as it would have been seen by inhabitants of the Bronze Age. Even the nearest star clusters in neighboring galaxies come to us through centuries and millennia. When we look up at night, we're reading a story written in light. Sometimes this light manuscript is also distorted by the gravity of massive bodies. This is gravitational lensing, an effect of general relativity. Thanks to it, distant galaxies can look like stretched arcs or multiply into several ghosts. If we boil it down to the essence, the sky isn't a frozen map, but a slow cosmic chronometer. Stars move, constellations are reshaped, and we always see the past in every ray that reached our eyes. You can observe stars without equipment, the North Star, an extension of the axis of the Big Dipper's ladle. Orion, 3 stars of the belt below, the nebula, M42, visible to the naked eye. With binoculars, you can see dozens of stars in the Pleiades, the Andromeda Galaxy, the double star Alberio, blue plus gold. A telescope will show Saturn's rings, moon craters, distant galaxies. Apps Stellarium or Sky Safari will show the sky in real time from any location. Stars aren't just lights, they're distant worlds, time capsules, the history of the universe. We see their past, but they're alive right now, and we're part of this story. Stars seem familiar. We study them in school, see them in telescopes, hear in the news about supernovae. But beneath the surface hide facts that don't make it into textbooks or popular videos. They make stars even more amazing. From vampire stars that steal mass to quark stars that may not exist, and from stellar earthquakes to stars rotating faster than sound. Here's a selection of little-known but verified discoveries, what astronomers talk about at conferences but rarely in the news. Many stars don't live alone, but in pairs. In such systems, one can steal matter from the other. If a dense white dwarf sucks gas from a companion, this is called a cataclysmic variable. When gas accumulates and overheats, a flash occurs. The star momentarily becomes much brighter, as if born anew. A classic example is SS Cygni, which explodes with amazing regularity. There's another type, symbiotic stars, a red giant and a white dwarf that slowly exchange matter. The giant sheds outer layers, and the dwarf absorbs them, forming a nebulous cloud around the pair. A famous couple is Mira, A and Mira B. One pulsates and ages, the other patiently collects its breath in gravitational nets, creating behind it a tail of gas stretching several light years. Even more spectacular stories, star collisions. In dense stellar clusters, they can literally merge. This happened with the object V1309 in Scorpius, first a flash, then disappearance. Two stars turned into one, bright, hot, as if rejuvenated. This is how blue stragglers are born, stars that look too young for their surroundings. There are also speed record holders. Some stars rotate so fast that their equators stretch to the limits of rupture. In the Tarantula Nebula, one such star makes a full rotation in a day. Its surface moves faster than sound in plasma. It holds together thanks to its own density and magnetic field. And among neutron stars, there are even crazier examples, pulsars that spin hundreds of times per second. Their rotational energy is colossal. No human technology compares. Some scientists assume that in the hearts of neutron stars, the pressure can be so great that even neutrons decay into their components, quarks. Then a quark star is born, a fragment of the primordial universe where matter exists in the densest possible state. So far, this is only a hypothesis, but several candidates for such objects have already been found. In short, stars aren't just sources of light. They're living, changing beings of the cosmos that can explode, merge, steal, rotate to the limit, and even peak into conditions that prevailed in the first moments after the birth of the universe. The sun vibrates, millions of modes of oscillations, like a bell. SOHO and SDO catch them. From vibrations, the structure of the core, the rotation speed of layers. In 1995, it was discovered that the sun rotates faster in the equatorial zone. The core is like a solid body, 25 days per rotation. In 2021, astroseismology, Kepler measured the vibrations of thousands of stars. In red giants, oscillations with amplitude and radii, most planets in the universe are similar to Earth, rocky, silicate. But there are others, exotic. In systems where stars contain more carbon than oxygen, true carbon worlds can be born, planets with a surface of graphite, carbides, and even diamonds. One of the most famous examples is 55 Cancri E, an extremely dense world where under colossal pressure, instead of water, layers of pure diamond form. The first known exoplanets were discovered not near a calm star, but near a pulsar, PSRB 1257 plus 12. In this system, 3 planets orbit a neutron star that emits regular pulses like a cosmic clock. Their origin is a mystery. Perhaps these are fragments of a destroyed star that gathered into new worlds. Among stellar clusters, M13 in the constellation. Hercules is especially impressive, a huge ball of hundreds of thousands of stars born at the dawn of the galaxy. Many of them are the second generation, formed from gas enriched by the ash of the first supernovae. At the center of such clusters, black holes of intermediate mass sometimes hide Omega Centauri, another giant cluster, is possibly the remnant of an ancient dwarf galaxy once swallowed by the Milky Way. Planets don't always survive the aging of their star. When it swells into a red giant, nearby worlds simply burn up or fall inside. Sometimes this happens even earlier. For example, Tabby's star surprises with irregular dimming, probably due to a dust cloud from a torn-apart planet. Another example, V Hydra. Recently it was observed how it swallowed its own planet and ejected into space a jet of hot gas. And somewhere on the edge of time existed the first stars, those that shone only with hydrogen and helium. They were giants, hundreds of times more massive than the sun, lived briefly, and died in superflares later called pair instability supernovae, the brightest in the universe. They were the ones who first seeded space with heavier elements. The modern James Webb Telescope is already finding possible traces of such ancient luminaries, pure spectra without any metals, from the depths of time just a few 100 million years after the Big Bang. Even among neutron stars, there are amazing creatures, magnetars. Their fields are so strong that they form real magnetic tornadoes that eject plasma into space. In some magnetars, the surface field seems weak, but in the depths, it can be incredibly powerful. One of them, SGR-04, 18 plus 5729, recently flared so strongly that its own rotation noticeably changed. All this shows how multifaceted the universe is, from diamond planets to stellar giants that flashed at the dawn of the cosmos, from pulsars to magnetars where physics is compressed to its limits. Variable Cepheids pulsate, changing brightness. But there are stars that produce sound in the radio range, pulsars like beacons. Vela pulsar produces sound when converting a radio signal. Astronomers recorded it like a cosmic bell, TESS-PLATOGAIA, mapping billions of stars. GAIADR4 will give parallaxes with an accuracy of 10 micro-arcseconds. We'll find stars from population 2 in the halo, blue stragglers, remnants of mergers, exoplanets in the habitable zone of red dwarfs. Stars aren't just plasma balls. They're vampires, cannibals, singers, earthquakes, diamond factories. They create elements, planets, time. And now we're returning. Slowly, as if from a warm cosmic cradle. Feel how your body again touches the earth, how your feet become heavier, your arms warmer, your breath deeper. You just traveled from nebula to supernova, from the first flash to the last breath of a star. You held in your thoughts a diamond white dwarf, heard the ringing of a pulsar, felt how heavy elements scatter across the universe and fall into your heart, into your bones, into your blood. You are stardust, and you're home. Now let all this settle, like quiet snow on a warm palm, like the light of a distant star arriving just now. If you want, go outside, raise your head, and tell one star, I know your story, and thank you for telling it. And I'm sitting here, finishing my tea that is already cooled. Outside the window, the same wind, the same star that called me this morning is still in place. You and I will meet again. Under the same sky when you want again, just close your eyes, breathe in, and the stars will come. Good night, or good day, or quiet cosmic breath whenever you're listening, until the next star.